Hello, everyone. So, I hope you all are doing good. Uh, in the previous lecture, I did explained about attention mechanism in detail, and we have also incorporated attention mechanism in our pre-trained architecture. We took project that is brain tumor as our test case, and there we have seen that how attention mechanism is helping us in getting the good detection or prediction. In our project we do have multi classes, and with the pre-trained model incorporated with multi-head attention. Multi-head, as I told, there are many attention mechanisms. So multi-head means we took 8 heads in our code. Every head is doing some mechanism, whether it is spatial, whether it is channel, whether it is self attention. So according to it, we focused upon the features, relevant features which are present in our data, and then we also added Gaussian noise so that I can have a diverse data, so model could learn in complex scenarios also. And then we also interpreted our results. We got good scores like 90% above accuracy we are getting with those architectures. Okay, so VGG 16, okay, VGG 16 and 19. These are the basic pre-trained models where it is having 13 convolution, it is having 16 convolution. Okay, plus 3 layers of your fully connected, and this one is also having plus 3 layers of fully connected. Okay, fine. The arrangement of these architectures, as we have seen, that it comprises of kernel that is 3 cross 3. Okay, and all the layers are arranged one by one. Okay, so the issue with this models, the drawback was that if we want to increase the architecture, if we go according to the 16 and the 19, definitely our image size is going to diminish. Okay, and we can't add more and more layers in a sequence. Also, they may lead to overfitting. Okay, and these models are complex in nature. Fine. Therefore, we want to have different architectures also to test our work. Okay, though VGG 16 and 19, along with multi head attention, we got the scores of 90% plus in accuracy with problem statements. Still, we want to look out for more architectures so that we can have further better results. All right, so let me share you my entire screen, and we will be discussing about the drawbacks first of these two architectures. Okay, and then we'll move ahead to Inception V3. So both these architectures are having high computational cost, like this much parameters are there in VGG 16, 138 million parameters. Parameters means weight and the bias. These are the parameters. Okay. Overfitting is an issue. Okay. If the parameters are more, counting increases, overfitting is going to increase. When the training data set is small, then the model is going to overfit. Inefficient feature learning, because we are having the fixed kernel size 3 cross 3. Every time when we do add a convolution layer, now we are having 3 cross 3 only here. Okay, and also while learning, while doing training, they may suffer with the problem of vanishing gradient. Okay, so they don't have any residual connections. Residual connection means I can't, like here, if I'm following with convolution, convolution. So what has been input here, and this has been outputted in residual or ResNet architecture. We do have a tap connection. Okay, so we do make a residual link in ResNet architecture. In case of 16 and 19, we don't have any like such kind of links available. Okay, so in this particular case, when we do perform the feature extraction, again we will add some portion like here by a residual connection. Okay, so that's not here. It's a drawback. Okay, and vanishing gradient is a problem like in deep learning, we used to update the parameters by this formula: w dash is equal to w minus alpha del L by del W. Okay, where L is the loss and W is the weight. Weight is one of our parameters. In case when the gradient is tending to 0, del L by del W is tending to 0, there is no update. W dash will remain as W, so you are not doing any learning here. So such kind of models faces a vanishing gradient problem. Okay, then they are absolute compared to the modern architecture. They don't have any advancements in their architecture. There is no like in basic, they are not having attention mechanism, depth-wise convolution, multi-scale processing, which can make which could make them efficient and versatile, but at the moment they don't have this thing. However, we have added the attention mechanism to them. What is depth wise, I will let you know. Okay, multi-scale processing, I will let you know. So we tried to improvise these architectures by adding attention mechanism. Initially these pre-trained models don't have that, so they are like less efficient. Okay, so in order to face this as a challenge, and now we switch to another architecture, which is better architecture than these pre-trained architectures, as Inception. So Inception is Google Net only. Okay, that is Google Net. Okay, Inception V1, V2, V3, V4. There are many variants. So what change they did in the architecture which will overcome the issues existing in the current architecture of 16 and the 19? Well, the basic model Inception V1 was introduced by GoogleNet in 2014, developed by Google. And here, when the multiple deep learning layers of convolution are used in a model, they have an issue of overfitting. I just told you. To avoid this scenario, Inception uses multiple filter of different sizes. First of all, see, it's not like that in a one go itself you will get all the solutions. No, we have to look out for the solution. That's what the research is called. So don't use in your architecture, because yesterday the question came, sir, how we can bring the novelty in our work, because we are the PhD aspirants and we want to have the publication. How we can bring the novelty? So okay, if you create an architecture, and in that architecture don't use this frequently, 3 cross 3, 3 cross 3, no, don't use this. You have to change the kernels, different size kernel. That is one of the suggestion. Okay, and perform parallel processing. Keep the layers parallel. Okay, so you got an idea that we can perform different kernel sizes. We can perform parallel processing. Just create an architecture which is designed parallelly. We can add attention mechanisms to them. Okay, so like here in Inception V1, the four parallel layers are 1 cross 1, 3 cross 3, 5 cross 5, and 3 cross 3 pooling. That is what they are having. 5 cross 5 was something which is objectionable because no, this 5 cross 5 kernel size is huge. So it's going to give you the complexity. All right, this is how they arranged parallel connection 1 cross 1, then 3 cross 3, 5 cross 5, and 3 cross 3 pooling. At least they took an initiative to solve the problem. All are in parallel. And then whatever be the results we are getting now, we are going to concatenate the results. That's what we do normally. Okay, fine. So they told inception V1 is naive form. The drawback here is even though 5 cross 5 convolution layer is computationally expensive, that is time consuming and requires high computational power. Okay, that an issue which is came in Inception V1 that was supposed to be good than the previous ones, but the computational complexity because of 5 cross 5 is more. So the authors or the researchers at the Google they added 1 cross 1 convolution before each convolution layer. So they put a change for faster computation. So before 3 cross 3, add 1 cross 1. Before 5 cross 5, add 1 cross 1. That's what you have to do. Okay, so add 1 cross 1 convolutions. Okay, got it. Now, this 1 cross 1 now, it's going to take each and every element. Okay, what is 1 cross 1 convolution? This is 1 cross 1. That means one element is only there in the filter. That's 1 cross 1. If this is your image matrix, okay, you have to operate it with 1 cross 1. So this will work over, okay, I'm going to get a result. This will be a result. Okay, then again it will operate over this. Again it will operate over this. Fine. So in this way I'm going to get the results accordingly. How the kernel works, you very well know there is a multiplication of element with the elements which are present here, and then it performs a sum. So they added 1 cross 1. 1 cross means only one element as a kernel. Okay, and this 1 cross 1 convolution before every convolution, which results in reduced dimension of the network and faster computation. Okay, so dimensions are reduced and computations got faster. Fine. This is how the diagrams look like, their architecture look like. This is the building block of Inception V1 model architecture. The Inception V1 architecture model was better than the other models at that particular time. At that time, 14, 15. Okay, and in comparison, this is the table. GoogleNet Inception V1 was having error rate of only 6.67%. Rest all are having huge errors, but GoogleNet was having error 6.67% only. VGG was having error 7.32. So that's why this architecture won the race of classification. GoogleNet. Okay, got it. Now, what makes Inception V3 model better? Now we have V1, then V2, then V3. So there are further changes in Inception models. V3 is advanced than V1, than V2. Okay, and it is much more optimized version of V1. In Inception V3 model, it uses several techniques for optimization, like it It is having higher efficiency. It is much more deeper model than V1 and the V2. It is computationally less expensive. It is using auxiliary classifiers. So these are the points now you have to remember how we can bring such things in our architecture so that we can increase the efficiency, we can reduce the computation. So those people who are doing the research, they have to note the points that I need to increase the efficiency of my architecture of the model, I need to reduce the computational capability computation. Your model should take less time to perform the computation. Okay, and this needs to be increased. And also you have to incorporate some layers from your side which can help in these two. That's what you have to do. Fine. So in 2015 this architecture V3 released with total 42 layer. So in VGG we were having 16 and 19, it is having 42 with a low error rate. All right. So how it make possible with adding 42 layers? Well, in Inception V3, what happened was it performed factorization into smaller convolutions. So if you are having 3 cross 3 or 5 cross 5, they are factorized into smaller ones. They are using spatial factorization into asymmetric convolution, like 3 cross 3 can be written as 1 cross 3 or 3 cross 1. So they are introducing asymmetric convolutions also, not only symmetric, asymmetric also. It's not mandatory. You may have a question, sir, can we use every time 3 cross 3 or like 5 cross 5 or something like that? No, it's not mandatory. They have used asymmetric convolution also. Okay, auxiliary classifiers and efficient grid size reduction that we will see. First, let's check out each and every point. Factorization into smaller convolution. Let's see here. So, for example, if we consider the basic inception V1, this is your V1. I already told you. Previously, V1 was having 5 cross 5, 3 cross 3. But later on, authors added 1 cross 1 and 1 cross 1 before 5 cross 5 and 3 cross 3. That was V1. Here, 5 cross 5 is expensive. So, to reduce the computational cross, the 5 cross 5 is replaced by 2 3 cross 3. Okay, so reduce. Okay, got it. One change. Instead of 5 cross 5, just incorporate 3 cross 3 and 3 cross 3. Okay, these two layers are introduced. That is one of the change. Okay, now to understand better, see how the process of 3 cross 3 convolution reduces the number of parameters that we already know. We have seen the working of convolution and how the filter do operate over the image we know. Okay, so if this is a 3 cross 3 filter, okay, and this is your, obviously it's going to map the image. So this is image, this is 3 cross 3 filter, this is 1 cross 1. Okay, fine. So from here to here you can see how the things got reduced. Okay, so as a result of the reduced number of parameters, the computational cost is also reduced. So this factorization of larger convolution into smaller convolution resulting a gain of 28%. Okay, so from this image to 3 cross 3, 3 cross 3 to 1 cross 1. Okay, much more better results. Also, asymmetric convolution. Even though the larger convolutions are factorized into smaller, but they didn't stop here. 5 cross 5 is divided into 3 cross 3 and 3 cross 3 too. But still, they got some option. Uh, they furthermore divided them into 2 cross 2. Okay, in fact, they also introduced asymmetric convolution. For 3 cross 3, they replaced it by 1 cross 3 and 3 cross 1. So, doing this, sliding a two layer network, the same receptive field as 3 cross 3. That means what we expect from 3 cross 3, same we are getting from 1 cross 3 and 3 cross 3. Okay, like this. You can see. This is 1 cross 1. Now, previously it was like, okay, see, check it out. How the things changed. It was 1 cross 1 with 5 cross 5 initially. This 5 cross 5 was later on changed to 3 cross 3 and 3 cross 3. Later on, this 3 cross 3 and 3 cross 3 are changed to 1 cross 3 and 3 cross 1. And this is also changed to 1 cross 3 and 3 cross 1. That's what they did. You can see. This is also 3 cross 3. This is also 3 cross 3, but not changed. Okay, here also 3 cross 3 is changed. Okay, that's what they are changing. Asymmetric convolution. So the structure of asymmetric convolution, the two-layer solution like this, 3 cross 3 to 1 cross 3 and 3 cross 1. They just perform two-layer. That means from 1 cross 1 go to 3 cross 3, then 3 cross 3 go to 1 cross 3 and 3 cross 1. Whatever be the results you are getting, just concatenate. Here also the same thing. They gave two-layer solution. That is 33% more cheaper than the same number of input filters if the number of input and the output filters are equal. It is much more cheaper. So after applying the optimization technique, the inception looks like this. This is how the inception look like. All these suggestions came that this is how you can change the filters. Okay, fine. So now next is utility of auxiliary classifier. That means auxiliary classifier. See, the objective of auxiliary classifier is to improve the convergence of deep neural network. The auxiliary classifier is mainly used to combat the vanishing gradient problem. Okay, so what these auxiliary classifiers are, we'll see in the diagram. See, these auxiliary classifiers result in many improvement in early stages of the training. Okay, and they act as a regularization technique to prevent the overfitting also. Okay, fine. So here, let's check in the diagram. Grid size reduction. Max pooling and average pooling were used to reduce the grid size. That is dimensionality reduction technique. In V3, to reduce the grid size efficiently, the network filters are expanded. Network filters are expanded. How the expansion has been done? We are having D cross D grid with K filter. After reduction, they are divided into D by 2 into D by 2 with 2K filters. This is done by using two parallel blocks of convolution and pooling. Later they are concatenated. Okay, again the changes has been done. Fine. So I guess you understood the initial changes related to the kernel. Okay, convolution. That's what you understood, that in convolution we are using the factorized kernels, we are using asymmetric kernels, we are also using here auxiliary classifiers. Okay, auxiliary classifiers to improve the convergence, to perform the classification. We are adding such kind of classifiers in our network. And also they told grid size, reduce the grid size. So for that particular reason, what they did here, this is mentioned. If the grid size is d cross d, we are having k filters in that. They are reduced to half, and the filters are increased 2k. Okay, so we are having a grid of, for example, anything 4 cross 4. For example, I am having a grid of 4 cross 4. Okay, 4 cross 4. This will be reduced to 2 cross 2, and the number of filters will be increased by 2k. Initially, if it was the filter was 2 initially, then it will become twice. Then it will be 4. 2 into 2 is 4. So the grid size is reduced half and the number of filters are doubled. That's what they are doing. Okay, so here it is, you can see. I am having 35, 35. Okay, so this is D cross D. This is number of channels. Okay, whatever you can say, filters, whatever. So this 35, 35 are divided by 2. 17, 17. Okay, 35 का half ना, that is 34 का 17 होता है, तो डोंट वरी, इट्स लाइक 17, 17. ओके, सो 35, 35 इज डिवाइडेड इनटू 17, 17, 17, 17. एंड ये जो 320, 320 है, दैट विल बिकम 640. And overall I'm getting after concatenation 17, 17, 640. So 35, 35, 320 is converted into 17, 17, 640. ये भी कर दिया उन्होंने. ठीक है, ये भी काम कर दिया. तो एनी हाउ दे आर ट्राइंग टू रिड्यूस द कंप्यूटेशंस, जो भी हो सके, वॉट एवर पॉसिबल ना, आप कंप्यूटेशन कम करो. ओके, तो फैक्टराइजेशन करो, असिमेट्रिक ले लो, एंड ये ग्रिड साइज वाला जो देर इज वन ऑफ द टर्म विच दे इंट्रोड्यूस दैट यू हैव टू डू. Okay, and this is the final inception model, which you can see here. After performing all the optimizations which we have done, so obviously you have to, in research, you have to find the optimal solution. Okay, you have to find the optimal solution. Okay, and this is how it looks, your inception architecture. Okay, fine. It takes the input as 2292293 and the output is 882048. 229 2293. That means width height is 229 and 3 is the RGB color and the output is 88248. That is what I'm getting, 2048. That's what I'm getting. Okay, fine. And the diagram which they have made here, it comprises of 42 layers. Okay, with convolution layer, pooling, max pooling, average pooling, concatenation, dropout, polygon, everything we are having. Okay, so this 229293 image will be converted into 8 into 8 into 2048. In case of our VGG16, we got it like 7 cross 7 cross something we got. Okay, and here we are getting 8 into 8 2048. That's what we are getting. Okay, fine. So, yes, here the detailed components of Inception V3 are mentioned. We are having convolutions. Okay, 3 cross 3, 3 cross 3 with a striding 2, 3 cross 3 with a striding 1, convolution padding with a 3 cross 3 striding 1. Okay, and that's what we are having. Okay, this is the Inception V3 table. Okay, fine. So, Inception V3, it is having less error rate as compared to other models. Okay, less error rate as compared to other models. Fine. And that's the reason we do use Inception V3 in our projects, in our uh, as a pre-trained model to perform the classification. Okay, now I need to talk something more maths related to the Inception V3. The terms, the changes, the optimizations which we did. Okay, here again I mentioned them separately. In Inception V3, factorization into smaller convolution, I told. Instead of 5 cross 3, 5 cross 5, you are using 5 cross 3 cross 3. That's what you are using. Okay, so 5 cross 5 convolution will build 25 parameters. 3 cross 3 will generate 18 parameters. Okay, so you might be asking a question, sir. Okay, this we understood. Ki sir, 5 cross 5 is converted into 3 cross 3, 3 cross 3. But sir, how it helps, sir? Here I am having 25 parameters to train. Here I am having 9, and let's take here also 9. 9 plus 9, 18 characters are required. So obviously now my model will not been taking so many characters, and that is the complexity of VGG 16 and VGG 19. They are having 135 millions parameters to get trained. Here I am having reduction in the number of parameters to train, low computational cost. As the parameters are less, operations are less. Efficiency is more with fewer resources. Spatial factorization also we did. We are not considering this 7 cross 7. Okay, not at all. Neither 5 cross 5. Let's okay. It is much more better if you convert 3 cross 3 into 1 cross 3 and 3 cross 1. Here also 3. Here also 3. 3 plus 3 is 6. Low. Furthermore, parameters get list. Okay, so decrease the computational cost for execution, and we are having small filters rather than the large filters. Okay, and it enhances the ability to learn distinct spatial patterns. See, spatial is what you are having now. This is spatial width and the height. This is a spatial. Okay, of an image. So by using different filters, you can cover up, you can patch up with this image. It's better to make the feature extraction by using asymmetrical kernels. Okay, distinct spatial patterns. Okay, and auxiliary classifiers are added to intermediate layers during the training to provide additional gradient signals and mitigate vanishing gradients. Like auxiliary classifiers act as a small network. Auxiliary, okay, they are acting as a small network within the main network and predict class labels independently during training. So आपने अपने architecture में, in your main architecture, you added some small components also, small architectures also, small network also. They are also doing some prediction. Okay, they do predict the class labels. So ये auxiliary तभी तो classifier है ना वो classifier can classify the class labels. Auxiliary means, okay, from additionally, in addition to your architecture, okay, you are adding your small architecture, small components. Okay, fine. So they they are discarded during inference, however, but the advantage is they helps to propagate the gradients to earlier layers, making training much more robust. Gradient propagation. Whatever be the calculation, training, adjustment in the parameters are been done, they should be propagated. Else, vanishing gradient. If the gradient is getting zero, then loss is like it's been zero. Then there is no training, no learning has been performed. It reduces overfitting. Grid reduction, I already told you. You have also seen like all these things. Grid reduction, just like downsampling the spatial dimension. D cross D is reduced to D by 2, D by 2, and number of filter are been increased. So with this, 2K will be the number of filter. One example we have seen related to 35, 35, 320, that is reduced to 17, 17, 640. Okay, so reduction in this grid size. Okay, it preserves the information, maintains critical features during downsampling. Downsampling कर तो रहे हैं, कम कर रहे हैं size. Okay, that's what we are doing. The grid का size है कम कर रहे हैं. Okay, but still we are trying to maintain the features, critical features. Okay, it improves the feature extraction and classification accuracy. Okay, fine, got it. So these are something which we have done, and I've also added some maths here, some operations I've added. Okay, so like this is the kernel size, this is the input image. Okay, and the operations for like which we do in standard convolution is this operation. If we do perform the factorization like 5 cross 5 is divided into 3 cross 3 of two convolutions. The operations which are performed by 3 cross 3 two convolutions are, this is your image, and 3 square into C intermediate plus again the same thing. Okay, so you have to multiply your image with the kernel. Again, image with the kernel. That's what you have to do. Okay, fine. So advantage is this, it's pretty much clear. 3 square is 9, 5 square is 25. Obviously, the computational cost is reduced. If I divide 25 by 9, 2.78. This much fraction, you are going to reduce the computational size. Spatial also asymmetric, all these maths now I mentioned here. I'll share these notes. You got an idea how it works. Auxiliary classifier, that means auxiliary classifier used in training to improve the gradient flow. These classifier add extra cost in the computation. कॉस्ट तो एक्स्ट्रा बढ़ाएगा, बट दे डिस्कार्ड दे गेट डिस्कार्डेड ड्यूरिंग इन्फ्रेंसिंग. The cost of auxiliary classifier depends on the number of layers in your network. कितने auxiliary use करना है, how many auxiliary layers, how many auxiliary classifiers you want to add, ये आप intermediate layer में आप देख सकते हो, you can do that. So these are like auxiliary classification, where this is the height and the width of the intermediate layer. C auxiliary is the number of channels, K is the number of output classes. This is the mass applied. Okay, fine. Grid size reduction. Now it's already, you have seen grid size reduction. Okay, fine. So we have covered all these things. I have mentioned separately also in terms of your like explanation what's the changes. And now the thing is, if you want to now we are totally focused upon spatial attention. Spatial attention. Okay, though obviously in my architecture I have uses multi-head attention, I will do that. But I thought that if I add special attention, how it's gonna, if you add spatial attention in the Inception V3, it will help model to focus upon spatial regions. In this entire changes which we did in this Inception V3, we are focused upon the spatial only. Okay, so factorization, by adding spatial attention to the factorized convolution, the model will focus upon spatial regions more. That is one of the change. Okay, then in asymmetric also, applying spatial attention in asymmetric will ensure smaller convolution, focus upon more significant region within the image instead of processing the entire image. That has also been helpful. Adding spatial to auxiliary can improve the ability to focus everywhere. Everywhere you are going to have a focus, 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 focus. Attention is just a focus. Just focus on the relevant areas in an image. That's it. With the grid reduction, whatever. So advantages of adding spatial attention is to focus on relevant features in the image, better feature extraction, reduce computational cost, increase the model performance. That's what we can do. Okay, fine. And yes, I can show you the code where I have used. For example, this is my chest X-ray classification project. Okay, this is my chest X-ray classification project, and here is my chest X-ray dataset. Okay, you can see this. This is just X-ray dataset. In this particular dataset, I am having four directories. You can see that is COVID-19, normal, pneumonia, and the tuberculosis. And obviously, like COVID-19, pneumonia, tuberculosis, they are challenging to classify because no, this just they will be filled with like that particular infection. Okay, so if you see the images of COVID-19, also here you can see the images of COVID-19. Okay, fine. And you can see the images of like pneumonia. Here the pneumonia images are there. Okay, fine. And here are the tuberculosis images are there. Okay, tuberculosis images. So obviously, all these three are the kind of infection which will cover the chest. Okay, and normal. This is the normal. These are normal image. That means clear. Chest is clear, then it's normal. Then we need to perform the classification here of these four categories. Okay, so how we can perform the classification? Okay, what approach I have used? Let me show you the code. What approach I have used? Well, this is my notebook and approach. I have already explained you in the previous classes also. I took my data. Okay, here I took my data. Fine. If you want me to increase the size, here you can see. Okay, all right. I guess not like this. Okay, I guess now. Okay, this is further reduce the size. It's not, you get reduce. Okay, I guess this is okay. So I took my data set. Okay, from the Kaggle. That's from where I am showing. Okay, and you very well know that I do make the data frame from this. So here it is. This is my data set path, and I am having four categories in this path. So same approach I followed in each and every project. Take the path. Okay, take the base path. Then create a list of as many as classes are present with you. You need to create a data frame, so you need to add these path individually to the base, and whatever be the files which are present in these, you have to mention in the entire path. So you will be making image path and the label. That's what you are going to do. Label will be the category, for example COVID-19, then normal, then pneumonia, and then tuberculosis. Okay, you can see here what I did. A very simple code. Explanation I've already given in the previous classes. This is my code where I created a data frame. This data frame I am having image path and like all these categories. Fine, that's what I am having. Okay, so all right, fine. Okay, let me increase. I think this increased. This increased the size. Okay, so after creating the data frame, what I did, you very well know that I do count the number of labels present with me. So here I am having 4,000 plus pneumonia, 1,500 normal, 700 tuberculosis, and 576 COVID 19 images I am available with. Okay, I made the count plot, I made the pie plot. Okay, I did displayed five images from each and every category. That's what you have to do. Okay, then I perform the label encoding. Okay, I need to give the labels like 0 to uh, initially I will give 0 to COVID-19, 1 to normal, 2 to like pneumonia, and 3 to your tuberculosis. Okay, so this is how I gave the labels. This is label encoding. Okay, and then I took only image path and the category. That means label encoded and the image path. Okay, now as we have already seen that your data is unbalanced. Okay, see again here, your data is unbalanced. Fine, highest number of images are of pneumonia 4273. Okay, now listen to me carefully. You are having unbalanced data. Okay, unbalanced data in which if you are having like pneumonia with more number of images and less number of images are you do have related to COVID-19. Okay, COVID-19, less number of images. So ultimately you need to perform the sampling. Yesterday the question came, sir, can we perform the sampling or can we perform the augmentation? Okay, sampling will, what it do is it will create the replica of the minority class equal to the majority class. That's what the sampling do. Okay, fine. Augmentation will help you to create new images. That's what augmentation stands for. Either you are having rotation, either you are having translation, either you can perform the flip, horizontal flip, vertical flip, whatever you want to, it will create the new images. Okay, so that's also a good idea. All right, fine. In my projects I did perform sampling because the reason is I already gave the explanation related to it. Because if you see the x-ray na, x-ray will be seen like in this way only, will not see the x-ray like in this way. Okay, rotate करके नहीं देखते कभी x-ray. We have to see it like in original view only. So sample करके I can increase the numbers. There is one more thing which I want to put a mark here. That sir, you are having different numbers. Okay, fine. So if you sample right now, you will create equal numbers. All will be equal. Then you will perform train test split. So it may happen that few of the images which are available in the training, which can also go in the testing because you have created the replica of the images. Okay, so because of the replica, the images will be duplicated, sir. Yes, 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 absolutely true. There will be duplication, and the kind of image which go in the training, the kind of image will also come in the testing, and that will give you scores good in training, testing both. But apart from the data which is not being present here, there your model can struggle. However, in my project I took this thing like approach, this simple approach only, that I performed oversampling. I performed oversampling without what? If you are having a data x comma y, you split it into x train, y train, x test, y test. Okay, so what I did is I oversampled this only. I oversampled this only. So I made all the class equal. After that, when I split it into x train, y train, x test, y test, so a image which is present in x, a similar replica of the image will go in test also. So model has already learned of this image. It will, if we give this image after the training to the model, it will detect easily. It will detect easily. I have done this approach. However, I will give you another approach also, where I haven't performed sampling of this. No, I first splitted the data, then I only sampled x train, this thing, these I sampled. I trained my model over this only, then I tested my model on test. That means in x test you will not get the replica of the images which are initially present in x. So both the approaches I am available with. Currently I'm using the basic approach. Okay, so I sampled, and now everything is 4273, everything has been there. I use imported all the libraries, and you rest, you very well know that I took VGG19 model. Okay, the entire architecture I have explained you previously. I took VGG19, I can take VGG16, and what you have to do in this particular project, just copy my model, just copy the entire architecture and just paste it. Copy and paste and just change VGG19 to VGG16. That's what you have to do, nothing else. So 16 will also be ready, 19 will also be ready, and here I'm having multi-head attention with 8 number of heads. Okay, so after performing this VGG19 weight download, you just reshape your image and then perform multi-head attention. And then add the Gaussian noise, global average pooling, and everything. That's what we have already seen in the previous class. Done. Okay, and then just train your model. I trained my model, and you can see the scores I'm getting is like nearly 98%. So much high accuracy, 98% accuracy with testing data. Okay, but I will give you another solution also with different project. I will show you right now. This is the confusion matrix. I'm already in a good state with the results. Already good state. Okay, fine. There is one more architecture I use. I haven't discussing right now about mobile net. Okay, this is my another project, spine X-ray, spine X-ray images. Okay, another project. You can see this is spine X-ray images. Let me show this. This is the data set. It's related to a research paper. Here it's mentioned. Okay, this description and any of the here is the general. Okay, general like this. It's related to some paper, spine X-ray. Here it is, plus one something like that. Here is a research paper. Transfer learning to detect scoliosis and like there is some name from the X-ray. Okay, here is the entire research paper for that. They have used another algorithm like UNIT. Okay, they have used this algorithm UNIT. Okay, and I have used my own algorithm, that is pre-trained model with attention mechanism. Okay, in this data you are seeing the images are like in 224, 227, 256, 299, and 331. This resolutions. So I took only one, this 331. This is 331. Okay, and here I am having three classes: normal, scall. Okay, normal, scall, and spawn. These two are the issues. Okay, these two are the issues. Okay, fine. Normal is just easy, and scall and spawn are the okay issues. Fine, and you can see the images. You can see the images. Whether I took normal whether I took this is call all these now images, like here this is call images, okay, and this is your spawned images. Okay, scroll, and this is your spawn images. Okay, fine. Okay, got it. So these are the three classes of images I am having. And now the code. What kind of code I did? This is again a multi-classification problem. What code I did? First, again, I took my data. Okay, I extracted the data from the Kaggle. Then approach is all the same. There is no change in the approach. Creating a data frame, counting, everything I did. Okay, I just created the data frame. I counted the number of images 17, scroll is 185, and spawn is 70. Very less number of images I am available in 331. I just took that particular only. Okay, 331, that folder images. So I'm having this much numbers only. Okay, and then I made the counter plot. Then I displayed the five images from each and every category. That's what I did. Okay, fine. I performed the encoding also without label encoder. I just encoded from my side only. Normal one is called two and spawned three. That's how I encoded. Okay, fine. So it's same. Either you can use label encoder, either you can create a dictionary from your side. You can label the images, label the category. Okay, after that, again, again after doing that, this is the number. 2 label 2 is 188, label 3 is 79, label 1 is 71 number of images. Here I haven't used random oversampling. No, here I haven't used random oversampling to balance it at this particular stage. No, I am having unbalanced data. Okay, doesn't matter. I imported all my libraries. I converted my label into string type. That is 1, 2, 3 will be converted into string. Then I divided my data, okay, into train, test, and valid. This is how I divided my data. Okay, first I am dividing my data into train, test, and valid. Okay, and then the training data. The training data, I am oversampling this training data. So the code which I am showing you right now is the preferred code for you all. You have seen in chest X-ray, I haven't done this approach. Okay, this I haven't done this approach. So you have a chance that there are common images in training and the testing. But here, in case of the project which I am showing you right now, if you are having unbalanced data, follow this approach which I am showing you right now. Okay, don't sample, don't oversample here. No, don't do this thing here. Instead, you divide your data into training, testing, and the validation, and then just sample training data. Just sample training data. That's what you have to do. Okay, training data, perform the resampling. Okay, got it. Fine. So this is what you are doing. And then next, what you can do, you can take you can take the images. This is the code where you are giving the image size pre-processing 224, three color channel. That's the same code which I have used in Chestrix also. Same code. Okay, so that's what you can take. Okay, and then you can use your GPU, whatever. Okay, and here I have used, this is my Inception v3 architecture, the one which I did explain recently. And what is the change I did? Instead of VGG 16, instead of VGG 19, I use Inception v3. The entire code is same. Just copy and paste it here and just change the architecture. Just use VGG, just use VGG 16, 19, and now just take it to Inception v3. Okay, got it. Same thing. Everything is same. Multi-head attention and all these. And with this architecture, I trained my model. Okay, I tested the scores also. Okay, and I got 79% accuracy. Now, sir, previously you were showing the accuracies of 90%, sir. 90% above accuracy you are showing previously. Now, sir, what happened, sir? एक्यूरेसी गॉट 79। तो सर थोड़ा सा ओवरफिटिंग तो शो हो रहा है सर, देर इज सम पार्ट ऑफ ओवरफिटिंग। ओके, अच्छा, एक रीजन ऑफ ओवरफिटिंग इज दिस, आई एम नॉट हैविंग दैट मच अमाउंट ऑफ डेटा। विथ स्मॉल डेटा एंड हैवी मॉडल ऑब्वियसली ओवरफिटिंग इज देयर, इसमें कोई शक नहीं है। There is no excuse if you are having a small data. How many number of images I do have? I am having very less number of images, 450. Okay, so obviously there will be an overfitting, वो होगा। बट प्रीवियसली क्या हो रहा था, व्हाट हैपेंड प्रीवियसली, वो सेम इमेजेस यदि चला जाता है इन ट्रेनिंग ऑल्सो इन टेस्टिंग ऑल्सो सेम इमेजेस, बिकॉज यू आर डूइंग ओवर सैम्पलिंग। सो ओवर सैम्पलिंग में यू आर क्रिएटिंग द रेप्लिका ऑफ द इमेजेस, तो सेम चला गया। इन दैट पर्टिकुलर केस ना एक्यूरेसी, टेस्ट एक्यूरेसी वाज आल्सो इंक्रीजिंग, वो भी बढ़ रहा था, हमें हम खुश हो रहे थे। We were happy by seeing the test score, test accuracy. But model already know about that particular image during training. Na, it got trained over that. Okay, तो score अच्छा आ रहा था. But here in case when I haven't exposed the images to the model, in that particular case with the less number of images also, though I got good score, 79 is not that much issue. Okay, it's also a good score, but there is some kind of overfitting here. ओके, कोई बात नहीं, कोई इश्यू नहीं है। एंड या दिस इज व्हाट माय कंफ्यूजन मैट्रिक्स इज फॉर दैट। ओके, दिस इज माय कंफ्यूजन मैट्रिक्स फॉर द इंसेप्शन V3 मॉडल। ओके, सो दिस अप्रोच यू हैव टू फॉलो, दैट डिवाइड योर डेटा इनटू ट्रेनिंग, टेस्टिंग एंड वैलिडेशन, एंड ट्रेन को बैलेंस करो, बैलेंस द ट्रेन एंड देन यूज द मॉडल। आर्किटेक्चर इज हियर द सेम। मेरे सारे प्रोजेक्ट्स में, आई विल शो मोर प्रोजेक्ट्स ऑल्सो। आई एम हैविंग ओवेरियन कैंसर क्लासिफिकेशन, आई एम हैविंग ऑटिज्म डिटेक्शन, आई एम हैविंग इसफोजियल कैंसर डिटेक्शन ऑल्सो। ओके, आई विल शो एवरीथिंग। ओके, तो आप ये सारा कोड मेरा एडिट कर सकते हो, यू कैन एडिट माई कोड विच इज अवेलेबल ऑन द Kaggle, एडिट शेयर्ड विद, लाइक करा है मैंने, यू कैन डू दैट। ओके, तो अब क्या हुआ, व्हाट्स हैपेंड सर, चलो ठीक है। yesterday there was also question asked to me, sir, we have trained our model, sir. Now sir, if we, in case we upload an image, so can model predict it? If we upload an image, can the model predict it? Yes, of course we can do that. See, let us suppose my model got trained, it's been ready. You do one thing, just take a image, upload a image, take a image, any of them, upload any of the image. Okay, let us suppose this is an image, this is the image path. You have upload a independent image of chest x-ray, brain tumor, spine, okay, this thing, okay, these x-ray images. Okay, so you can upload any of the image, this is the path of the image. You have to convert it into 223. Okay, that's what you have to do, that is the image size. And after converting that into image, particular image, just convert it into array and then divide it by 255 to normalize it, and then expand the dimensions. That's what you have to do, convert it into this particular resolution, because you have trained your model on this resolution only. 3 channel, okay fine, no, not an issue, not an issue, 3 channel, क्योंकि वो ग्रे स्केल होगा तो भी 3 channel if you do now, or it will remain the same. So just convert it into this thing, then this thing, then this thing, and expand the dimensions, and then just give that image to the model for the prediction. Just give the image to the model for the prediction. Here the model which I've used is DenseNet. Okay, you can use Inception V3 also, which was trained above. Okay, in prediction, after once I got the predictions, np.argmax. Argmax, why? Because we are having multi classification. So in multi classification, we get the probabilities. For class 1, this is the probability. For class 2, this is the probability. For class 3, this is the probability. The one which is having the highest probability, that will be considered. You can print it later on. Here it's printing. Here I'm printing. Okay, so the prediction has been done, and the predicted class which was found is class 2. The predicted class is 2, predicted label is 3. Okay, predicted class is 2 and predicted label is 3 for me. Okay, so you can see here what is the class. What is the class for the image? Okay, you can see what's the class for the image. Class 2, class number 2. You can see here above. To whom we are calling as class 2. Here, here you can see this is label 1, 2, and 3. We gave three labels. Okay, one to normal, two to scald, and spawned 2, 3. Three labels we have given. Prediction we got class 2. See the answer. Predicted class is 2. Predicted label is 3. What does it mean? What does it mean? Predicted class. Obviously, now. Obviously, you are having 0, 1, and 2. So this is your class. So according to that, the labels defined are 1, 2, and 3. Third label. The class was of, that means this third label. Label number 3. So the class whom we gave the label number 3 is the answer. Okay. So it's quite easy that you can, with this, I already told previously also, with this set of lines, you can perform the prediction from your side also. Okay, got it. So that's one of the project. Again, another project. Let's talk about ovarian cancer also. Here also I am having the ovarian images available. Okay, and you can see like one, two, three, four, five, five images. Again, multi classification. What you have to do? Just follow my same code. Nothing. Just follow my same code. Obviously, I will be accessing the data. I will be converting into data frame. I will be displaying the count plot. I will be displaying the pie plot. I will be displaying the five images, and then I will be performing the sampling of my data. Okay, in order to balance it, and then I'm going to use a pre-trained model with attention mechanism. That's what I'm going to do. Okay, here you can see. Okay, here you can see that. Okay, I've used Inception v3 again. Okay, I've used Inception v3, the architecture which I've explained you. Uh, Attention mechanism I changed. I used differential attention mechanism that I will explain ahead, hopefully tomorrow. Okay, and the concepts of attention QKV I already explained you. Okay, so it's just like same only, not so much hard and fast. Okay, I'm having the number of heads, I'm having the key. Okay, I will be take QKV. Okay, and I'm going to map the image over QKV. Okay, I will going to take the different attention score. So that's what the attention is. Instead, it's better that you can take multi-head attentions. That will be much more better here. Okay, yeah, please say. Yes, Subhashish. Yeah, I just explained thoroughly only. Just in a quick differential attention. Here, number of heads, number of dimension. So you have to build QKV from the TensorFlow. Okay, just build
So
QKV and just
I
call
was
this
saying not
QKV.
to keep the
Yeah,
class tomorrow. That's it. Not.
yes,
I
yes.
was talking about not to keep any class tomorrow. That is what.
Okay, okay. No worries. All right. So we are just using the same kind of concept related to the attention only. As you can see here, the query key and the value, we are using this thing only, along with the attention scores related to it. And we are applying, see, calculate the attention score, perform the shortness activation function to get the final attention score. Okay, and then you have to perform one more operation, that is calculation of sparse attention. That is being attention score multiplied by TensorFlow dot casting attention scores to this particular operation, like attention scores greater than TensorFlow reduce mean of the attention score. Just applying a basic formula to perform, like what I say, as I did now previously also, what I say, normalization, like just like a normalization. That's what you have to do. So create the sparse attentions and use them. That's it. That's differential attention. Okay, however, when I use the differential attention now, the scores which I was getting previously was not, here you can see only 70%. With multi-head attention, I got 90% plus. But with differential attention, I haven't got that much score. I'm having 70% score here. Anyhow, that's a kind of an approach which I use just to differentiate my work from the previous work of multi-head attention. I use differential attention. Okay, this approach, differential attention, I used. Okay, but you can see I'm not getting the good quality scores. One more thing I want to mention here: the input shape here I took 224, 224. That should be 299 and 299. Okay, one more thing I want to clear: in case of inception, now, in case of inception, they do demand for the shape of 299, 2993. Okay, it doesn't deny that if you take 224, you can take 224, but the more relevant thing in inception is you have to take 299, 2993. That's what you have to do. So in order to make 299, you have to above in pre-processing here. In pre-processing, kindly mention the image shape as 299, 299. ओके, यहाँ पर ये काम करना, यदि इफ यू आर डूइंग VGG 16, VGG 19, तो ठीक है। ओके, बट जब इंसेप्शन यूज कर रहे हो, इफ यू आर डूइंग द इंसेप्शन, तो 299 कर लेना। 224 पे भी देर इज नॉट एन इशू, बट स्टैंडर्ड में आप करें तो दैट विल बी मच मोर बेटर। एंड मल्टी हेड अटेंशन यू हैव टू यूज हियर। ये डिफरेंशियल को नहीं करना, मल्टी हेड है तो यू आर ऑलरेडी अवेलेबल विद द कोड, जस्ट कॉपी पेस्ट हियर, दैट्स इट, नथिंग एल्स। विल गेट द स्कोर्स, गुड स्कोर जहां मिल जाएगा। ओके फाइन, तो मल्टी हेड अटेंशन व्हाई इट इज हेल्पिंग, you have already notified the reasons, and this is much more better architecture inception. The reason: we are having factorization of the layers, we are having asymmetric layers, so इसने computational complexity कम कर दी। That's what it did, reduce कर दी इसने computational complexity because of these two. ओके, एंड अटेंशन यू आर ऑलरेडी यूजिंग, तो अटेंशन में तो उसको बेस्ट फीचर्स मिलना है, प्रॉफिटेबल है। ओके, अगेन आई कैन से दैट प्लीज डोंट यूज अटेंशन विद आफ्टर ईच एंड एवरी कन्वोल्यूशन। ओके, कन्वोल्यूशन देन अटेंशन डोंट यूज, ऐसा नहीं करना, नहीं तो कंप्यूटेशनल कॉम्प्लेक्सिटी इंक्रीज हो जाएगी। ओके, डोंट यू डू दिस थिंग। ऑलराइट, आपका पूरा द एंटायर जब आप पूरा कर लेते हो, व्हेन यू गॉट द वेट्स ओके फ्रॉम एन इमेज, आप खुद का भी सेल्फ आर्किटेक्चर ऑल्सो यू कैन मेक, वो भी मुझे बताना है। विल बिल्ड अ स्मॉल आर्किटेक्चर वेयर वी आर गोइंग टू गेट द गुड स्कोर्स, दैट ऑल्सो आई एम expecting. Okay, where you can just add convolution pooling, like this you can make an architectures, and you can add multi head attention, you are going to add Gaussian noise also. Okay, और अभी suggestions I already gave कि क्या करना चाहिए आपको इंसेप्शन में। we got an idea that kernel size less ले लो, asymmetric also you can take, grid size भी कम कर दो। दैट्स व्हाट यू कैन डू, पैरेलल अरेंजमेंट करो इनका, पैरेलल, तो यू कैन हैव बेटर थिंग। यहाँ से सीखा। Okay, so I am having so many projects here. This is my ovarian project with Inception, and this is autism detection project. Autism का challenging data था, और in autism detection the data was so much challenging. Well, let me show you. I am having images of autism. This is autistic images. ये आपको कुछ यू आर अनेबल टू सी एनीथिंग बिकॉज इट्स ऑल ब्लैक. ये this is autism image. And and if I show you non autism images, these are non autism images. ये भी वैसे ही है ब्लैक. ये तो और ज्यादा चैलेंजिंग है. हियर डूइंग अ सेपरेशन ड्यूरिंग डूइंग अ क्लासिफिकेशन इज वन ऑफ द टफेस्ट चैलेंज. कैसे कर लोगे? इट्स ऑल ब्लैक. यू कैन सी ओनली थिंग सम सिग्नल्स. ओके, सम सिग्नल्स यू कैन सी हियर. बाकी तो पूरा ब्लैक है. ये चैलेंजिंग था autism. Anyhow, but मेरी approach was same. Again, I took my data. Okay, and after taking my data, I did perform the same thing like as I was doing. The number of images, like I was having 1971. Okay, initially the number of images which I was having was already 50-50% already था, तो मुझे encode करने का जरूरत भी नहीं था. Okay, I don't require to balance the data. It was just like 1971 or 1968. Already my data was balanced, but still वो मेरा code में था, तो I did perform the balancing. Label encoding भी कर दिया. Okay, that's what I did. And then I applied algorithm that is inception v3. See, here I applied inception v3 again with the differential attention. Okay, in differential, let's take the number of heads. Let's take the dimension की. तो यही तो अपन ने मल्टी हेड में भी करा था. The one was asking me the question कि सर वो थोड़ा सा समझा, तो यही करा था आपने. When you refer to your multi head attention, वहां भी आपने number of heads लिया है और की का dimension लिया है. की dimension. If you want to clarify you this thing, आप देख लो. ये आपका ये वाला differential का कोड है. And you can take the code of ये रहा. ये आपका चेस्ट एक्सरे का कोड है. इन चेस्ट एक्सरे कोड सी मल्टी हेड अटेंशन, नंबर ऑफ हेड्स 8, की डायमेंशन इक्वल टू नंबर ऑफ चैनल्स. Okay, so same thing here in my code also. Key dimension, that's the number of channels. Okay, so just assign the values to them. Then you have to build the input shape. तो input shape क्या होगा? What is the input shape? Input shape is the image shape. ओके, इनपुट शेप इज द इमेज शेप, और इमेज के शेप को ही तो आपको मैप करना है. दैट्स व्हाट यू हैव टू डू. यू हैव टू मैप द इमेज शेप विद क्यू के वी. दैट्स व्हाट यू हैव टू डू. ये मैपिंग करनी है आपको. एंड हियर यू विल बी हैविंग डब्ल्यू क्यू, डब्ल्यू के, डब्ल्यू वी. दीज आर द वेट मैट्रिक्स. ये होगा, तो यू हैव टू आइडेंटिफाई दीज वैल्यूज. And how you are going to identify? Q equal to I dot W cube, K equal to I dot WK, and V equal to I dot WV. This is how you have to identify. So अभी यहाँ पर ये वैल्यू भी ले लिया कोड में. This is also mentioned here. According to the input shape, you have to create the query key and the value. Okay, then you have to call and identify what is Q, K and V. यहाँ से कैलकुलेशन होगा. अटेंशन स्कोर्स कैलकुलेट होंगे. attention scores are calculated. Short mass activation function is going to apply over it. ये लगा लोगों के. एंड उनका ये वेटेड सम है. दिस इज द वेटेड सम. तो अटेंशन स्कोर कैलकुलेट करा, नॉर्मलाइज करा, एंड ये एक फॉर्मूला है अलग से जो लगा दिया इन ऑर्डर टू मल्टीप्लाई. अटेंशन स्कोर को कास्ट करा है इनटू फ्लोटिंग पॉइंट टू क्रिएट अ स्पार्स. ठीक है, दैट्स समथिंग व्हिच वाज बीन डन. एंड वेटेड सम निकाला है. बात खत्म है. यही है बस. तो यहां वाई, अच्छा क्या स्कोर मेरा? लेट मी चेक द स्कोर. व्हाट स्कोर आई गॉट? व्हाट इज द स्कोर आई गॉट फॉर द ऑटिज्म? 77. See, I require multi head because a single head is not capable enough. Single head is not capable enough to extract the features from the images. Definitely we require, क्योंकि मुझे स्पेशल फीचर्स को अटेंड करना है. ये डिफरेंशियल से मेरे को आई एम नॉट गेटिंग सो मच प्रॉफिट्स, बेनिफिट्स नहीं हो रहा मेरे को. तो मल्टी हेड लगा दूं यदि मैं, इफ आई कैन अप्लाई द मल्टी हेड, आई कैन हैव सम बेटर रिजल्ट्स. ओके, yes Subhashish, you got this thing or not? Yes sir, ask the question. Yes Cooper sir, you are having some question. Am I audible or not? Okay, so anyway, I just use this differential attention also, but you can apply multi-head attention. Here the training accuracy was like a good one. Yes, sir. Any question, please? Training accuracy was good. Okay, I was keep on increasing, but the testing accuracy is 77%. Same thing we have seen here in ovarian cancer also with differential attention. Like or like it's like a weighted attention only, not so much I feeling the difference.
I, I had a question.
Yeah, yes, sir. Please, sir.
So maybe I missed something on the autism, but autism is a behavioral disorder, and I'm confused as to what information is coded in the black images that would inform us about autism.
Yeah, yeah, sir. These images, na, for autism, these are neurosignals, sir. What I know, these images, na, are neurosignals. Okay.
Taken from
Take
imaging or EEG, or what
sir,
kind of
with some
information is coded?
sir with EEG, sir, with EEG. These are some neurosignals. Okay, like some with like EEG, the device is connected, and I think with related to eyes. Okay, how the person is seeing, something like that is there. Okay, so
Okay.
such kind of signals are created, sir. Okay, sir. So and this data was not available on the Kaggle. This data I took additionally. It's related to some research. Okay, and then I made the code based upon it. Okay, so with differential attention, I got 77%. However, with multi-head, I'm damn sure that you will get better scores. Okay, Inception V3 I used. Okay, you can use one more architecture mentioned here as like, let's see, exception. Okay, I am having esophageal cancer detection also. Okay, so what's present with esophageal? Okay, this is like okay, CSV file I am having. So in CSV file, not that much. You want to work over the images, so I think that's not an issue. Okay, so esophageal, we are going to work over the images. So let's talk about the images only. Okay, fine. So autism, ovarian cancer, then so many projects I am available with. Spine I also show, chest X-ray shown, brain tumor I have shown. Okay, and these three, VGG 16, VGG 19, Inception also. And if you want to see the implementation, let's show you the implementation also. This is the implementation of Inception. I am having a 1 cross 1 filter, 3 cross 3 filter, 3 cross 3, 5 cross. See, 3 cross 3 reduce. This is 3 cross 3. This is 3 cross 3 reduced. This is 5 cross 5 reduced. This is 5 cross 5. So 3 cross 3 reduced will be like 1 cross 3, 3 cross 1. Okay, so let's take 1 cross 1 convolution, then 3 cross 3 convolution. In 3 cross 3, you have to take 3 cross 3 reduced and 3 cross 3 original. Then 5 cross 5 reduced. 5 cross 5 reduced means 3 cross 3, 3 cross 3. And original 5 cross 5. Then pooling. Okay, then we have to concatenate all. And this is how we are going to build the inception. Okay, like convolution 32, 32, 64, all 333. Then convolution 11, 33, 33. And then these, ye to, see, this will be the initial layers. Next, these are parallel, which we have created above. They will be parallel. Okay, so inception module. This is a inception module. I will call this module here in building the inception. Okay, this architecture will be called here in building the exception. You have already studied the concept, no need to worry about. Okay, but this is a architecture built from scratch. Okay, you very well know what is this 3 cross 3 reduce means, 5 cross 5 reduce means. Okay, so 5 will be reduced to 3 cross 3, and 3 cross 3 will be reduced to 1 cross 3 and 3 cross 1. That is the reduction. Okay, so the entire this inception module will create a block. I will start initially from these layers. Till here, it's all like go one by one. After that, I will be calling the inception module. This module, okay, one time, two time, three time inception modules are called. Then pooling layer. Then one time, two time, three time inception module is called. Then global average pooling layer. So after this all, I'm going to take the weights from the inception, then I'm going to add the multi-head attention, then I will perform the global average pooling, then drop out Gaussian, Austrian, everything I'm going to add. Input size of the image will be 299. Got it. This is how we have to use. And you have to go through the architectures that I have made this from, like, okay, this will help you. You can modify this architecture by checking the shortcomings, because if you talk about what better we can do in our researches, we want to bring the novelty in our researches, obviously you have to follow the suggestions which are given in these architecture, then only you can build your own architecture. There is a question now, sir, what we can do. Obviously now you can perform parallel, arrange the convolution layers in parallel. How you can arrange in parallel? This is the inception basic code I will give you. Okay, spatial dimension. Okay, kernel convolution. Okay, so this is what you can do. Attention, I already told you. Multi-head attention. Okay, Gaussian noise, you have to add. Fine. That's what you have to do. And obviously, computational complexity. Anyhow, you have to reduce this computational complexity. Accuracy needs to be increased. That will be a novel architecture. Activation function which we are taking here is ReLU. Every convolution is having ReLU activation. Kindly do change if it is possible. Take swish activation function. Let's try with some other activation. Instead of ReLU, just try with any other. Just here it is swish. Take exponential also if it is possible. Take something else like if it suggests like logic gates, NAND, NOT. Make these as an activation function. Just see how things are going. Okay, if you can add two to three novel things in the architecture, no new things in the architecture, that is an upgrades. Okay, and check its computational complexity, check its accuracy. If you are better, obviously you have done with your point. Show the computation, show the maths. In research, in publications, you have to show the maths. This was WHC. After doing all these, we got this is the computational complexity, this is the accuracy. Make a comparative table of 4 to 5. Take the resources, these are the resources used, these are the scores I got. Use mathematical formula, include algorithm, include the layers which you have used and what they did, some new approach. Fine. So inception v3 architecture with multi-head attention giving good score, with differential not giving good score, differential its average score. Okay, then there comes one more architecture which is better than inception. One more architecture which is better than inception, that is exception. Okay, exception architecture. See, exception like it's extreme inception. Inception we are done. V1, V2, V3, V4. V4 is not that much famous. It haven't gone that much famous. Till V3 it's okay. Then exception came. Exception is a deep learning model developed by Francis. Again, Google. All these are Google product. And the inception architecture utilizes inception modules. Thus, I have shown inception modules. These are the inception modules. Okay, this is an inception module where you are performing parallel processing, parallelization of the layers. Okay, that's what you are doing. You are performing parallelization. Okay. However, in case of exception, what they are using? Let's see. Okay, in exception, the model replaces it with depth-wise separable convolution layer. Depth-wise separation. Depth-wise. Okay, so I'm going to explain you what is this depth-wise separable convolution. Again, new approach has been followed. So it is having total 36 layers. Inception V3 was having 42 layers. This exception is looking like a short version of Inception with better score. So it is having 36 layer in total. When we compare with exception to Inception, it only slightly performs better on ImageNet. However, on large data set with 350 million images, exception perform better. So we are using depth-wise separable convolution. That's the difference. What is this depth-wise? Let's talk. Depth-wise separable convolution is a type of convolution operation designed to reduce the computational again. इसके बिना तो कुछ है ही नहीं ना. We don't have anything beyond that. Computational complexity reduced, number of parameter reduced, number of the accuracy should be increased, performance should have to be increased. So in standard convolution, where we do take the image with the spatial dimension, width and the height and the channel, uh, okay, where a 3D kernel slide over the image, 3D kernel, 2D kernel, it slide over the image and produce a result, a tensor result. Okay, that is computationally expensive. Depth-wise separable convolution means was depth-wise separable convolution splits the convolution operation into two steps. We are dividing convolution into two steps. Step number one, a single 2D filter is applied to each input channel separately. That means this captures spatial features within each channel independently. If the input has C channel, each channel is processed by K cross K kernel. This operation reduces the computational cost. See, listen, you are having W H C, width of the image, height of the image channel. This depth-wise convolution is saying that you have to process channel. If the input is having C channel, then apply kernel over this channel. That is the step number one. Step number two, a 1 cross 1 convolution is applied over all the channels to combine the output of the depth-wise convolution. That means then after performing this thing, for every channel, for every channel, you have to apply, first for every channel, you have to apply kernel and then apply 1 cross 1 to mix the information across different channels, learning channel wise relationship. We'll see what's happening. So in computer vision deep learning, AlexNet was the initial, like first was the Lenet architecture given, then this was 3 layers, then AlexNet came which was having 5 layers in 2012. Okay, for CNN. After AlexNet, the trend of using convolution was increased by coming like VGG, Inception, all these things increase. Okay, and the Inception module which we have learned, this is our Inception module. Okay, where we are having parallel convolutions. Okay, we give input and these are parallel convolutions. After we are concatenating the concatenator, just now we have seen this thing, parallel convolution. A standard convolution layer tries to learn in a 3D space, namely width, height, and channel. That is 3D. However, Inception module divides the task into spatial and cross channel correlation using filters of different sizes. That's what inception do. Okay, it perform parallel processing. Just now we have seen. Okay, it divides spatial and cross channel correlation, like this cross channel. Okay, this is our previous layer, and this is what we have seen in the inception, and then concatenation. Okay, however, exception model takes even more aggressive approach. It entirely decouples the task of cross channel and the spatial correlation. That means spatial and cross channel decouple. That is called as extreme inception model. Okay, here it is. For example, if you are giving a leaf image, okay, leaf image to the kernel, it perform pointwise convolution, and then this is depth-wise convolution. Depth-wise, what is depth? What is depth? Depth is what? Depth is what? It's a channel. So every channel we need to perform the convolution. That is called as depth-wise convolution. Okay, for every depth we need to perform the convolution. That is called as depth-wise convolution. Okay, here you can see, and then later on you are going to combine the results. That's what you have to do. Okay, fine. So this exception architecture, this is the exception architecture. What we are doing, we are having entry flow, we are having middle flow, we are having exit flow also in exception. Okay, so here is the entry flow. We'll take convolution 32, we will take convolution 64. This is separable convolution. Separable convolution. Then pooling. Okay, so we are taking separable convolutions here to reduce the computational complexity. Okay, so let's see what is this. Let's have a few more discussion related to this particular topic. I will elaborate more, no worries. This exception module perform depthwise separable convolution before dividing the individual components of exception. This depthwise convolution divides the entire process into two. One is depthwise, one is pointwise. Depthwise means there is a single filter, that is your kernel. It is applied to each channel separately. How many channels you are having? C number of channels. For example, you are having an image like 7 cross 7 2048. So there are 2048 channels. This kernel is applied to every channel. That is called as depthwise. If an image is having three color, RGB, so a separate filter is applied to each color channel. That means for uh, red this filter, again filter for green, again filter for red. Every channel you have to apply a filter. That's what you have to do. And then later on, this is pointwise convolution. After depthwise, a pointwise convolution is applied. That is, pointwise is 1 cross 1. Pointwise is 1 cross 1, that combine the output of depthwise into single feature map. This is what it do. Okay, so for example, let's see. You are having, this is a depthwise this is an chest X-ray image. Let us suppose you are having RGB image. So I am having a red, I am having green, I am having blue. RGB, I am having three channel. So I am having this three channel. I will be having this kernel, this kernel, and this kernel. I am having three different kernels which are going to apply over each channel. And whatever be the results I'm going to get, I'm going to concatenate the results, then I'm going to apply 1 cross 1 convolution over it to get the final pointwise convolution. That's what I'm going to get. Okay, so instead of performing like as we have seen now in case of inception, they perform depthwise convolution. Exception utilized slightly modified version. In original depthwise separable convolution, we perform depthwise convolution, then pointwise convolution. The exception model performs pointwise convolution and then depthwise convolution. Means first it perform one cross one, then depthwise. That's what exception do. That's what exception do. So these things now we have to remember. All right. So what we have covered so far? We have covered the use of inception V3, inception V3 plus multi-head attention. The code is all same. I have also shown you inception V3 with differential attention. However, the things were just like same as we have used in multi-head, but that's a single head. This is only one head. Okay, in multi-head we are getting a good opportunity. Inception, you are having like parallelism, factor of kernel, asymmetric kernel, reduced grid size, auxiliary. That's what you are having. Okay. However, just now I have introduced exception. Exception. Okay, you are having two things. One is depth-wise convolution. One is point-wise convolution. Depth-wise convolution, if you are having as many as number of depth, you have to apply the kernel over that much number of depth. Three color RGB. So apply filter here, here, here. You have to apply the filter, and then pointwise, one cross one. However, in exception, they told that first pointwise is applied and then depth is applied. That will explore more. And again, here also I'm going to add multi-head attention at the last. That's what I need to do. Okay, fine. Okay, so I guess, well, that ends my efforts for today's class. Okay, let me stop presenting. Let me stop recording also.